Okay, now we're going to talk about eigenvalues, eigenvectors, and a characteristic polynomial. So this is section H9I. Um, and if you want to get some of the videos that I use to help me make this video, I recommend looking at Eigenvectors and Eigenvalues Simply Explained on YouTube, or you can look up Professor Dave Explains um, Finding Eigenvalues and Eigenvectors. Much of what I use in my video I got from those resources, and there's a few other resources you'll see in Canvas. So anyways, we've got a image here 3 comma 4. So I'm going to just put 3 comma 4. Oops, right there on both of these, 3 comma 4. And so far we've learned about matrices and transforming like a point, for example. So if I've got a point 3 comma 4 and it undergoes a transformation like this, we could see where is it going to go. So I'm going to call this here A prime. We're just doing a review right now of what we've done before. So I've got 3, 0, 0, 3, and what happens when I multiply my matrix, my transformation matrix to my point, which we write as a vector. A vector is simply a 2 by 1 matrix if you really think about it. Anyways, if I multiply this out, I get 3 times 3 plus 0 times 4. And then the next row is 0 times 3 plus 3 times 4. And so I get 9, 12. So my new point 9, 12 goes over 9, up 12. Okay. And I'll call that A prime. Okay. And then same thing here. We've got, oh, why did I call that A prime? Oh my gosh. Okay. Okay, so once again, this is A. And then, so we're going to do the transformation. We've got our transformation 1, 0, 0, 2, my transformation matrix, and I'm going to apply it to the point 3, 4. And once again, I do my transformation, and we end up with 3, 8. So the new point is right there. Okay, so that should be review. So now, instead of transforming a point, we're going to think of transforming a vector. And so we're going to multiply a matrix times a new vector. So here I've got my transformation matrix, and I've got a vector. So if I multiply this matrix 1, 2, 1, 0 times my vector 2, 2, 0, we end up getting 1 times 2 plus 2 times 2 in the first value, and then I have 1 times 2 plus 0 times 2, which simplifies to 1 times 2 is 2, and 2 plus, so that's going to give me 6, and then this is 2. So my new vector, so here's the old vector. I'm going to do that in blue. And here's the new vector, 6, 2. So it means I go over 6 and up 2. Okay, so my transformation to this vector has taken me to this new point. This new point is 6, 2. Okay, And let's do the same thing. We're going to do the same transformation, 1, 2, 1, 0. 1, 2, 1, 0. And I'm going to do this transformation to a different vector. 2, 1. Okay, so I'm applying a transformation matrix to a vector, and I end up with 1 times 2 plus 2 times 1. And then I have 1 times 2 plus 0 times 1. And so that matrix becomes 4, 2. And that's my new matrix that I get. So once again, I'm going to highlight the old matrix 2, 1. That's the old matrix 2, 1. And my new matrix is 4, 2. So that means I'm going to go 4 to the right and up 2, right? And if we look here, these go in the same direction, don't they? So we're going to talk about right now is if the result vector is in the same direction as the original vector, it is called an eigenvector. So this new vector here, 4, 2, is an eigenvector. This pink one is not in the same direction because it's not parallel to it and it's not the same direction. So this is not an eigenvector, and this one is. Okay? And eigenvectors, we use the symbol lambda for eigenvectors. Okay, so you're going to be seeing this symbol a lot. Okay, so so in our example that we just did here, so here we had our matrix, we had our transformation matrix, right? We call that matrix A. Okay, that's a transformation matrix A. This here is our vector. I'm going to call our vector x with a little line and a little arrow. Okay, so here we have our matrix A. We've got our vector, and when we multiplied our transformation matrix to our vector, we got 4, 2, didn't we? Okay. Now, what we learned in chapter 3 about vectors, this, since everything is divisible by 2, I could factor out a 2, and we can have a scalar, right? And then here is our original vector. I'm going to call that x. If it's going the same direction, it's a vector. So this right here is our eigenvector. And this value right here is our eigenvalue. Oops, I messed up here. This is an eigenvalue. Sorry about that. That's an eigenvalue. And so this value right here, the scalar, is an eigenvalue. Okay, so here we have the matrix times the vector is going to also be equal to the eigenvalue times the eigenvector. You may want to hit rewind to think about that. This is deep. So we've got our matrix times the vector is equal to the eigenvalue times the eigenvector. So let's determine if this vector multiplied by this matrix is an eigenvector. So let's multiply this matrix. 1, 2, 1, 0 times this matrix, 3, 1.5. And then I get 1 times 3 plus 2 times 1.5. And then we get 1 times 3 plus 0 times 1.5. And that simplifies to 6, 3. Okay. So our original vector was 3, 1.5. And our new vector is 6, 3. So I'm going to go over 6, up 3, over 6, up 3. And oops, and we see that, yes, it is an eigenvector. And we can also tell that I can, compared to this one here, you can see it's twice as long, isn't it? So I could rewrite this here as 2 and 3, 1.5. Because now I've got the original vector, and I've multiplied it by 2 to get this. So what we have, I'm going to write it over here. What we have is our eigenvector is equal to 3 and 1.5, and our eigenvalue is equal to 2. Okay, and remember, our eigenvalue is a scalar. This is important. And this here is a matrix. A is a matrix. So something important to keep in mind. We've got our matrix times the vector is equal to our scalar times the vector. Important to keep that in mind. So let's do one more example. Determine if this is an eigenvector. So we can multiply our matrix -3, 1, -2, 0 times our vector 1, 1. And we end up with -3 times 1 plus 1 times 1. And then we have -2 times 1 plus 0 times 1. And that gets us -2, -2. So let's plot our original vector. Original vector is 1, 1. Right. And then our new vector is -2, -2. So -2, -2 is right there. Let's use a ruler. It was so sloppy last time. So you can see it makes a straight line. Even though it's the other direction, it is still an eigenvector. Yes. And so our eigenvector, this is -2 times 1, 1, right? So the eigenvector equals 1, 1. And our eigenvalue is -2. going to start using the symbol here because this is the symbol we use for eigenvalue. Okay. Okay, so now we're going to learn how to solve some eigenvectors and eigenvalues. So everything I'm going to write down right now came from Professor Dave's explanation video starting at 2.55. He does add a few things that are a little confusing, but for the most part, this is what he said, and he says it very articulate and amazing. I wish I was as articulate and amazing as him, but I try my best. So, here we go. So we're going to start off with, we've got our matrix times our vector equals our eigenvalue times our eigenvector. Now, before we even get started, this is a matrix. This is a scalar. So you can't say that A is equal to lambda. You cannot say that because the A is a matrix and this lambda here is a scalar. And a scalar is not a matrix. But we can use the identity matrix to help us. So our identity matrix is 1, 0, 0, 1, if you can recall that from our earlier matrix introduction. So if I've got an identity matrix 1, 0, 0, 1, we end up with the matrix we originally started with. So we're going to be using this, and we use the letter capital I for representing identity matrix. So we're going to be using this identity matrix to our advantage to help with this here. So first of all, before we even get started, if I subtract this right side, if I subtract lambda x on both sides, I end up with a minus equals 0, right? I can subtract that on both sides, and then I'm going to insert the identity matrix here, so that now I've got a and the reason I can do that is the identity matrix times a matrix, a vector matrix, is just going to be its identity. And now I can use distributive property, because I couldn't use distributive property to factor out the A and the lambda because they were not they were not the same. I couldn't do that. But if I have the identity matrix in there, I can factor out the vector. So then I end up with the A matrix minus lambda identity. And so I've able to factor out the eigenvector. Now, we're not allowed to make the eigenvector equal to 0. Okay, and I'm just going to leave it like that. The Professor Dave goes into great detail on why we can't make this equal to 0, but I'm just going to leave it at that. So in order to make this left side equal to 0, we need to make the square matrix A minus our eigenvalue identity matrix, we need to make that equal to 0. So in order to do that, we have to make the determinant equal to 0. Okay. So I'm just going to say A is equal to A, B, C, D. Just right now we're just deriving the formula. Okay. So and if I have the identity matrix is this, then lambda times the identity. Oops. Lambda times the identity is going to be equal to lambda 0, 0, lambda. Okay. So now I'm going to use these two things, and we're going to find the determinant of matrix A minus lambda identity. Okay, so I'm going to replace A with our generic A, B, C, D minus, and we just said lambda I. I'm going to replace that with lambda 0, 0, lambda. And if now this is matrix subtraction, so I can do that inside here, and then I end up with the first spot is A minus lambda, A minus lambda. The first row, second column would be B minus 0. I'm just going to write B. And then I have C minus 0. I'm just going to write C here. And this last spot here is going to be D minus lambda. So I'll write D minus lambda. And I'm going to have to make this determinant equal to 0. Okay. And so what I just did was I just derived this A minus lambda, B, C, D minus lambda. So when you have these absolute value symbol things here, that means taking the determinant of that, or taking the determinant, and we're going to make the determinant equal to 0. So I'm just going to read through this here. So we know the determinant of this is not going to be equal to 0 for there to be a unique solution. So we're required to make our determinant of this equal to 0. Now, in this example, in this here, I have lambda I minus alpha, and over here I have alpha minus lambda I. It doesn't matter the order, because when you take the absolute value of it or subtract it, it's going to cancel out anyways. Okay. So I'll let you read this on your own, but after you take the determinant, the result is going to be a characteristic polynomial. I'll talk about that in just a second. And we will only be doing 2 by 2 matrices in this course. Okay, so now let's do an example with some numbers. Okay, so we know that we need to make, we have I, and we need to make the determinant of this equal to 0, right? That's what we just did on the previous page, right? We need to make this equal to 0. So let's do that. A is 1, 1, 4, 1. And I'm just going to write this as lambda 0, 0, lambda. Okay. So if I simplify that, I get, we can do subtraction of the matrix and put it into one thing, and we get 1 minus lambda. The second space here is 1 minus 0. I'm just going to write 1. Here, do 4 minus 0. I'm just going to write 4. And then this spot, I'm going to do 1 minus lambda. Okay. And if I put these absolute values things, that means we're going to do the determinant. So to take the determinant, I'm going to take this times that, 1 minus lambda, times 1 minus lambda, minus, and then 4 times 1. 4 times 1. And that has to be equal to 0. Okay, so now I'm going to FOIL this out. 1 times 1 gives me 1. 1 times negative lambda gives me negative lambda. Negative lambda times 1 gives me negative lambda. And negative lambda times negative lambda gives me positive lambda squared. And then we have 4 times 1 is 4, so minus 4 equals 0. Okay, I can simplify this a little further, put things in the correct order. So I got lambda squared minus 2 lambda, and 1 minus 4, that's going to give me negative 3 equals 0. And this right here is our characteristic polynomial. Okay, characteristic polynomial. In some books they call it the characteristic equation. So if you hear me say characteristic equation or characteristic polynomial, this is what we're talking about. And so we use the characteristic polynomial to help us find the eigenvalues. And that's what it says right here. Okay, so let's do this. So we can factor out our characteristic polynomial equation. And I can see that I can write this as 3 and 1, negative and positive. So now that I've factored this out, I know that my two eigenvalues will be 3, and the other one is going to be equal to negative 1. So these are the two eigenvalues. Okay, and I think I'm going to stop this video and then make the next video. So I'm going to be using this example here and on the next problem, and using these eigenvalues on this problem. Now we're going to find out the eigenvectors. So I'm going to make a second video right now.